shared underneath the notes. So you would find this tomorrow. If you look at 3.3 notes, you just print it underneath that, you'll find the work here. And the reason I really started to do that is because we were never finishing in 7th period because they're 7 minutes shorter than us. So it's just going to get posted, and if we don't get done with their class, then they're just responsible for watching the video for anything that they missed. So either way, we can use it however we want. So what chapter 3 now gets into is all the rules of derivatives, so that we don't have to use the big long limit as h goes to 0 for every single function to find their derivatives. There are shortcuts for all these, so we can kind of expedite this process a little bit. So if you kind of look at our table here, you'll see different ways to define a function. Oops, wrong thing. F of x, g of x, we can call h of x, whatever, and then we can just use a regular old y. We'll do things like first derivatives. We've already talked about this a little bit. One, the tick marks, another tick mark, or the whole dy dx notation. Okay, I'll review. We can also go and take a second derivative. We really could go 3, 4, 5 derivatives, but if we ever do a second derivative, notice how there's 2 tick marks for these, and then 2 tick marks for these. And then the exponents correspond to the number of derivatives. So if we ever use the fraction notation, the dy over dx notation, the exponents will indicate how many derivatives I'm asking you for, or how many derivatives that represents. Okay? So the first little rule, the most basic, I think some of you did this last year, the easiest rule that we can deal with is the power rule, to where if you look at, if this is our function, and you have an exponent of n, all the power rule is saying that we need to do is multiply the exponent by your coefficients. So that's where this comes from. And then whatever that exponent is, you're going to subtract 1. All right. So for this one here, this first one, I'm going to have you use this fraction notation first. So when we take the derivative of this, we're going to write this as dy over dx. You also could just put y primed. I think that's ultimately kind of what we do because it's shorter and easier. But since this is a y function written with respect to x, we're finding the change in y with respect to the change in x. So we'd put dy over dx. And the power rule just says you're going to do 7 times 11, which is 77. And then we're supposed to, if we look up here, subtract 1 from the previous exponent. So instead of an x to the 7th, we subtract 1, you just get an x to the 6th. That's our power rule. All right, pretty simple. If we go to number 2, same thing, dy over dx. You're going to do 3 times 4 is 12. Subtract 1 from that power, so 12x squared. Plus this current exponent would have been a 1. So you're going to multiply 1 times 2, which is 2. And then you would subtract 1 from the power, which would give you a power of 0. And then since we all know that a power of 0 is a 1, it really just means your variable drops out. So we just get a plus 2. All right. One of the things to be careful of, even if you think this would never happen to me, what I do see a lot of is people mess up the negative exponents, or when there's an exponent in your denominator. So when you see this 1 over x squared, I would recommend bumping that up, writing it as x to the negative 2. It's a better visual. It helps keep our signs straight. And then it's still the power rule. So we're going to multiply 3 by the coefficient. So you just get a 3. Subtract 1 from that power, so x squared. When we do now this as a negative 2 times the coefficient of a negative 1, that should turn this into a positive 2. And then our new power, when we subtract 1, should be a negative 3. We do typically want positive exponents, so we would want to simplify this. So instead of 2 times x to the negative 3rd power, we are going to put that into your denominator as 2 over x to the positive 3rd power. Four, same thing. Just be careful with fractions and negative exponents. Those are the things that people just tend to make little mistakes on. It's kind of the algebra more than anything. So this is really just a 1/3. So if I do 9 times a negative 1/3, that should give me negative 3. The 9 reduces with the 3. And then our new power should be an 8. So negative 3x to the 8. 3 times your 2/3 should just give us the 2, so minus 2, and then x squared. All right. Now, one of the reasons I want you to use fraction notation so we understand how it would change once our variables start changing around a little bit. So since this is now, how is our y changing? Like how far up and down are we going? but we're now doing this with respect to a different variable of u. So the fraction notation for a derivative, we would now write this as the change in y as it compares to our change in the variable u. So you'd put dy over du. Go through the power rule, pretty simple. I think at this point we probably got a handle on this. And then 25u to the fourth plus 8u and then plus 5. Then 6, nothing new. I just give you another one with a fraction and a negative exponent. Because again, as you're sitting there thinking, I won't be the person to screw up the negative exponents, there's a reasonable chance at some point you do. People just tend to mess these up a lot. So it's now back to y written with respect to x. So our vertical change is being measured in y still, so dy. Our horizontal change is back being written in terms of x. So change in y over change in x. And then power rule again. So negative 6, x to the negative 3, minus 4, x to the negative 2. Throw some positive exponents in there, and then drop them back into your denominator, write them as positive, should be good. All right, we're going to move on, though. Rush things a little bit here. All right, what's even easier than that rule is our constant rule. So we can read it, but let's talk about why this is. If I ask you what is the derivative of this, and we understand that derivative means slope, think about what this graph is. If we just did y equals 10, recall how that's a horizontal line up here through 10. And then recall what you've known for many, many years now. What is the slope of a horizontal line? Yeah, okay, see some zeros up. Well, now we know slope is your derivative, or derivative is your slope. It doesn't have a rate of change. It's constant. It's always a 10. So the derivative of any constant right here, we use the tick mark now, is just a 0. So whenever we go and find the derivative of a constant, it's a 0, because it's really asking what's the rate of change of this constant, and it wouldn't have a rate of change. Uh-oh, that's not good. See, even format's bad. Was this a pi, if I remember correctly? Pi squared on your paper? Okay. Just keep in mind pi is a constant as well, so don't think you're going to do 2 pi to the first. Pi squared is 9.5-ish. It's a number. So this, again, just has a derivative of 0. Yeah, this did format really weird when I downloaded it. So this one, let's rewrite this real quick. X to the negative 3, x to the negative 8, and then plus a 4. So now it's a combination of our two rules. So the first couple are just our power rule. So we do a negative 3, x to the negative 4, minus 8, x to the negative 9. So each one of them is its own rule. But then when we get to that constant, we would do plus and then ask what's the rate of change of 4, what's the slope of a constant, and there isn't one. So then that really just drops out. It's a 0. Throw some positive exponents, okay, put them back in your denominator, and then that's our answer. All right. Last one, 10, super easy. We'll just do y prime. You can do dy dx also. It's y written with respect to x, and we would get 12 x to the 11th. That's the power rule for the first term.
I can't see your screen.
You can't? Oh, no. Oh, yeah. I'm getting a message there. I don't know what happened. That one you can do. Should get 12x to the 11th, right? As a final answer. Not much going on there. Okay. Should be sharing out now, I hope. Can we see it now? Okay. So those are really, really simple. These aren't necessarily hard, but what you will find over the course of the next chapter, just a lot of rules get thrown on top of some more rules. And the first kind of big rule that I don't know if you've seen it or not, is called the product rule. So the reason it's called a product rule, notice how we have product between two different binomials here. Same here, this binomial is being multiplied by that binomial. So we have two different options. You could, if you want, we could FOIL this out if you want, and then just create a polynomial like we were dealing with up here, and then just go term by term if you want. We also have what's called the product rule. So whenever we have a product between two different functions, so u times v, you'll kind of see our little rule here. U and V are the two terms we're multiplying together. You'll see we want the derivative of U, so the U primed means we want the derivative of the U, and then the V you're going to leave alone. So we would take the derivative of the first term, leave the second term alone. Then you would add, leave the first term alone, and then take the derivative of the second term. So you're doing the derivative of one, leaving the other alone, plus, and then you basically flip that combination around. So if we were to look at number 11, this is F, so I'm going to write this as F primed of X. Hopefully I can squeeze this in. This is considered our U, this is considered our V, our first term and our second term. So we want the derivative of the first term, so 18x plus 4 from our rules above. The second quantity we just leave alone, so you just rewrite it. Then you're going to add, I'm already running out of room, leave that first term alone now. And then we multiply it by the derivative of the second term. So that would be 3x squared, minus 10x. All right, we follow that. Now, for the sake of, even if we were in school, we had a full 49 minutes, and we weren't remote, and we weren't already falling behind, I wouldn't have you simplify this right now. Just leave that as your final answer. That'll keep you busy for a while if you're going to FOIL all that, add up all your terms. Just know the logistics of how the product rule plays out, okay? 12. I would again take a few seconds to just rewrite this. I think it's worth your time so we don't mess up the positive and the negative signs. Let me make this bigger. All right, and here we go. So derivative of the first. So that should just give us 2. The negative 2 and the negative 3 would make 6. X to the negative 3. Rewrite the second one, unchanged. And product rule we always add, and then you just flip that combination around. So now the first term you rewrite. And then we want the derivative of the second one. So this would be a negative 1. X to the negative 2. And then when we do this, the negative 3 and the 4 make a negative 12, x to the negative 4. Okay, we good with all that? For the sake of time and how our current life and world is right now, we're not going to worry about rewriting that with negative or with positive exponents or simplifying it even further. We'll move along. What the product rule will really be used for, just so we're kind of aware, because there's nothing stopping us from just multiplying all those out and then doing the power rule. But eventually, if we get to functions like x sine of x, where there's a product between those, or if you have e to the x times the sine of x, then you have to know the product rule. It's easy with these to just kind of multiply them out. We could FOIL all of them. But once you start getting into some different types of products, then you're going to have to know that rule. So right now, we wouldn't necessarily do this very often, but certainly when we get to these, the product rule will pop up a lot. So if there's a product rule, then you're all bright enough to kind of know, then we probably also then have a quotient rule. There you go. Computer's lagging today. So the quotient rule is what you would think it would probably mean if we have a quotient, which is a fraction. So if we look here, here's our fraction. And we want to take the derivative of a function with that's a rational expression. Here is our rule. So kind of understand how this plays out now. V is your denominator, U is your numerator. So if we look, the U stays the same, so your denominator stays the same. U was the numerator, we want the derivative of the numerator. Quotient rule we subtract, and then we leave our U alone. So notice how the U doesn't have a tick mark, so you're going to take whatever the original numerator was, rewrite it. V prime then is the derivative of your denominator. And then all of that gets divided by your denominator getting squared. This very first year, many, many years ago, I threw this on there because it was in one of the books. And people actually really like this and use this a lot. The order is important with the quotient rule. In the product rule, it doesn't matter. So there's nothing stopping us from taking this combination and flip-flopping them. So when we do the product rule, we really could do this combo and this combo flip-flopped. And the reason we can do that is because you're adding. The order is unimportant. When it's the quotient rule, you have to do these in the correct order. And when we get to a test, a multiple choice test, one of the always distracting answers is if you get these flip-flopped. So the whole low D high minus high D low, the low implies your denominator multiplied by the derivative of the numerator, the high term. Then we're going to subtract, the high term is your numerator, and then we want the derivative of your denominator. And then all over your denominator squared. All right. You're going to get a bunch of derivative rules, so that's a nice thing to kind of get down to keep the quotient rule straight as we start layering more and more rules on you over the next few weeks. All right, so with that, go to number 1. I'm going to make this big so my monster handwriting might fit. There. Right over here. So for this one, we use F prime notation. So if you notice, V is your denominator in our formula. The V is unchanged initially. So it's your denominator, unchanged. So we just rewrite it. Multiplied by the derivative of your numerator. So these are our old rules from the front page. And then minus. Product rule we add, quotient rule you're going to subtract. We now switch that combination around. Now you leave your numerator alone. So we recopy the x to the 5th minus 3x to the 4th. And we multiply by the derivative of your denominator. So the derivative of x squared plus 7x would be 2x plus 7. One giant fraction bar. And then that gets divided by your denominator squared. As I mentioned before, it's unlikely I would have you multiply all this out. Sometimes we do. Certainly right now, with our restrictions, we're not going to. Just know, again, how all those kind of work out. All right, so with that, try number 2 real quick. Just go through that one. We have to remember our rules from the front page, the power rule. And we now have our quotient rule. How does this play out? What in the world happened there? I got booted. Right, hopefully you were working well as requested. And now my screen's all messed up. I'm not sharing now though. No, I'm not. Okay. So let me share. All right, I think we're up and running. Just enough time for you to throw this down. Okay, so quotient rule is your denominator unchanged. So x squared plus x to the 6th multiplied by the derivative of the numerator. So 3x squared minus 8x to the 7th minus the top. And then the derivative of your denominator, 2x plus 6x to the 5th. All of that then with the big fraction bar gets divided by your denominator unchanged. We just square it out. And for right now, we're just leaving that.
On a test, would you want us to like simplify all that?
It would depend. And if I did want you to simplify that, it wouldn't be quite as much algebra to where this problem is going to take you 10 minutes to get all done by itself. It would be much simpler. Actually, you're going to have to do that in number 3. Just because of the type of question I'm asking, you're going to find I ask you to simplify a much shorter and simpler expression. Okay. Okay, so now with number 3, people usually love this one when we're together. because this one now, if you see the double ticks, is asking you to take two derivatives of this equation. Okay? All that really means is we need the first derivative first and foremost. Once we have the first derivative, you're just going to turn around and take the derivative of that. So go to work on the first derivative. That's something right now I would think most of us are pretty comfortable with. And I'm going to create some space here. This one we will want to clean up a little bit as a general rule. And again, it's general, so not necessarily always the case, but generally speaking, when we're trying to find a second derivative, which we are here, you want your first derivative to be completely simplified before you get into your second derivative. So now in this case, I can't see who asked that question because my screen's messed up right now. But whoever asked that asked if you're going to have to simplify. Now you're going to want to simplify this because we want to clean up that numerator and our denominator so it can make our second derivative a little easier to work with. So now, still one tick mark here. All I'm going to do is simplify the numerator. So we'll distribute the 3, 15x minus 9. Understand how this is playing out. Not only is the negative getting distributed to this quantity, but it's also getting distributed by the 5. So we're really taking a negative 5 and distributing to the second quantity. So we should get a negative 15x minus 25. The denominator, we're going to want to square that out. So go ahead and simplify your denominator. So that should give us a 25x squared minus a 30x plus 9. You would then recognize in the numerator, hopefully, that we have some like terms that we're going to be able to combine to simplify that further. So we would see the x's are going to cancel. So the 15x and the negative 15x cancel. You end up with a negative 9, negative 25 to give us the negative 34. And then our denominator, we rewrite. That's our simplified first derivative. Once you have a simplified first derivative, then it's okay to move along to our second derivative. And all that is, if this is our simplified first derivative, that's now what you're taking the derivative of. It's still a fraction, it's still a quotient. So we still need to do the quotient rule. Denominator first, so 25x squared minus 30x plus 9 times the derivative of your numerator. Mo, is that your brother in the background there? My screen's all messed up. You're like this big right now.
Hey, Mr. Pena.
You want to learn again? You want to teach the class?
Yeah, light work.
Yeah, this is right. Yeah, do my light work. What's that?
Can't teach you as well as you, though.
Oh, you'd be all right. You'd be all right.
I missed you. How you been?
I've been good. Missed you too.
That's good.
Yeah.
Staying safe?
Who's better at math, you or Mo?
You tell him.
Yeah, we'll find out, right? We'll find out.
Yes, we will.
All right.
Have a good day.
Thank you. You too. So now be careful with this. We're taking the derivative of the numerator, and that should be a 0. That's a constant from the front page. When we do the derivative of any constant, it's going to be a 0. Then we're going to subtract, leave the numerator alone, so you're going to get a minus negative 34. And then the derivative of your denominator is 50x minus 30. One giant fraction bar. Square your denominator. This whole first term in the numerator is gone because you're multiplying by a 0, so this would all go away. Don't worry too much about simplifying. We're not concerned about that right now. So we end up with a positive 34 times that 50x minus 30. And then all divided by the 25x squared minus 30x plus 9 quantity squared. Don't square out that trinomial. That will also keep you busy for a while. All right. So those are our four big rules that we start with and that you'll see all year. So you want to have a pretty good handle on those. All right, so number 4, similar, just different ways of asking these questions. So it says, suppose u and v are differentiable, so that means their derivatives exist, and they're functions of x. So that would simply mean like u might be x squared. Don't write this down necessarily. I don't know what these are. I'm just making it up. But u is a function of x, and v is a function of x. We just don't know what they're equivalent to at this point, but we know they're written in terms of x. We know that u of 1 is 2, u primed of 1 is 1, v of 1 is 5, and then v primed of 1 is a 4. And then what I want you to do is find the following values of the derivatives at x equals a 1. So when you look at this here, this notation was one of the ones that you could have put on your quiz and your test. What this is, this is called an operator. Whatever is inside of your parentheses, this expression is telling you to take the derivative of that. So if you notice, we have a product right now, so we want to take the derivative of that product. So it's just a different way of testing you on the product rule. From the front page, the product rule is the derivative of the first term, so u primed. We don't know what that function is, so we can't actually take a derivative, so we're just going to mark it with our tick mark. We would then leave the v alone. So whatever v was, it's going to stay the same. Product rule, we now know we're going to add. And then we switch this combination around. We now leave the u alone. We just recopy the u. And we take the derivative of the second term, which is v primed. You were told you're going to evaluate these at the x value of 1. So what that would mean is we want u primed of 1 multiplied by v of 1, and then u of 1 multiplied by v primed of 1. These are then the values that you're given up here. So now we can just look up here. These are the values that I gave you. We just substitute them in and then evaluate that so we get our answer. So u primed of 1 was a 1. V of 1 was 5. U of 1 is 2. And then v primed of 1 is a 4. Simplify that, we should get 13. All right. Okay, try B. Just the product or the quotient rule now. See if we got the order down. Okay, and then see what we have here. Quotient rule, whether you're doing just using math words, denominator multiplied by the derivative of the top, or the little phrase low d high, we should have the denominator v multiplied by the derivative of our numerator. Quotient rule, you're going to subtract. The numerator gets left alone, derivative of your denominator. All that then gets divided by your denominator squared. At this step, these are the values that we have up here, so you're just substituting those in and evaluating them. So we do that, and hopefully you have your answer. We'll see if we agree. So we would get what? -3/25. I'll agree with that. Good. A lot of heads shaking yes. And last one. Letter C. I shouldn't say last one of these anyway. As a little hint also, this does not equal 5, so don't get 5 for that answer. Okay, so here's what you have to understand about this one, because it's very easy to think the derivative of 7b is 7, the derivative of 2u is 2, and then throw down a 5 for your answer. Typically, that's what I see a lot of when we try this problem. If we're in class, I'd be calling on people to see what we get, and I would get a lot of 5s. What you have to understand is v is some function of x. So come up here to this v. It would be some function of x. If I actually did v primed, you would still have a 2x plus a 2 right here. Same with u. U is some function of x. So we would get, in this case, u prime to equal a 2. We don't know what these things are for this problem down here. So we don't know that the derivative of v would give us a 1, because up here it clearly did not. Up here it clearly did not. We just don't know what those derivatives are. So all you're doing with this, and this is a nice rule to kind of understand as well, when you have a coefficient, we're just dropping the coefficient of 7. And then just like over here, when we did the derivative of v, didn't we write a v primed? And whenever we did the derivative of a u, didn't we just write a u primed? It's the same here. So the 7 drops, and we're just going to multiply that by the derivative of v, whatever that might be, because we don't know. Minus, drop the 2 down, and whatever the derivative of u is, which we don't know, that's why we've just got to use the notation u primed. This is now the expression that we're going to evaluate. This is easy from here. V prime we know is going to be a 4, and then the u prime value we know is going to be a 1. Simplify that, we should get a 26. All right, any questions on that? Sometimes that's a head scratcher for some people. Does that make sense? Good. All right. We might almost finish here. 5 is, yeah, let's see where we're at. So number 5. See if you, so part of the problem just in general, as we move along throughout the course of the year, is reading a problem and even understanding what the question is asking. Try that right now. Like read number 5. We know everything you need to know, I promise. I'm not teaching you anything new right now when we do number 5. Whether from last year, anything we've talked about, you know everything you would need to know to look at number 5 and be able to attack that problem and do it. So take a second and see if we could process that and see if you understand what this is now asking in the context of calculus and what we've been doing here the last week and then definitely today. If you're not sure, don't go too far, but if you think you're on the right path, then knock yourself out there. Okay, let's see where we're at. We're a little short on time here, so I want to make sure we at least get this one done because you're going to get one similar on your homework. So the key little phrase here that should make you think a little bit, because I haven't necessarily talked about this just yet, is the idea of horizontal tangents. But you should have some background knowledge on what horizontal means. We've certainly been talking about tangents recently. You would have talked about tangents in the past. So what this alludes to is I can make a tangent line anywhere on this graph. So if I put a dot right here, I can draw a tangent line to this curve. I could put a dot right here, draw a tangent to the curve. I can do any point on the curve, draw a tangent line in. And this is what this graph does look like if we put it into our calculator. What we want is a horizontal tangent. How many would we have just by the visual on this graph for this answer? I'm seeing some, yeah, okay. Seeing some threes held up. There should be three, right? I could put a dot right here, horizontal tangent line. I could put a dot right here, horizontal tangent line, and I could put a dot right here, horizontal tangent line. So in terms of what this question is asking for, it's asking for these three spots. Those are the answers to the question. The other thing that you've talked about with horizontal, and we can see it with our lines here, what do we know the slope of horizontal lines are? 0. And what word do we now use for slope? That's now a fancier calculus word that we now have the tools to do. All right, and that's derivative. So if we took the derivative of this, which is now very short and sweet, so that's the derivative of our graph. This gives us the slope of our line tangents at any x values. What we want to know is, at what x values will our slope actually give us a value of 0? From here, we can now solve this. We'll pull out a 4x, that's our common factor. We'd be left with an x squared minus a 2. Continue factoring. So it's not a perfect square, but we could definitely do x minus root 2, x plus a root 2. Anything's a square of something, right? So we can do x minus root 2, x plus root 2. And notice how we now get one answer right here as at x equals 0. That makes sense if you look at my graph. We get another answer right here as a positive root 2. And then we get the third and final answer as a negative root 2. Okay, makes sense. All right, big picture 6, we don't really have time to do it, so we're probably going to stop there. Just now keep in mind, and there's the bell, just to reiterate that point, just keep in mind, you have an assignment due tomorrow. I will probably send out a remind message, just so you know and you don't forget. That is found on your home page. So as soon as you go to our, that's not what we do. As soon as you go to your home page on our Canvas page, it's right underneath those notes. So this is the worksheet on this stuff. So if you were to grab that, print it, or just reference, if you look at the computer, if you don't have a printer, just write it down on a sheet of paper. All right, get that uploaded to me by tomorrow, and then if you have any questions, we can talk about it also. Okay? All right, that's all I got. We made it, barely. Have a good day. We'll see you guys tomorrow, okay?